We're asked to determine the chromatic numbers of the given graphs. The chromatic number is the smallest number of colors needed to get a proper vertex coloring, where a proper vertex coloring of a graph G is the assignment of colors to the vertices, such that all adjacent vertices have different colors. Looking at the graph on the left, we have a complete bipartite graph. A graph is bipartite if the vertices can be divided into two sets, A and B, with no two vertices in A adjacent and no two vertices in B adjacent. Let's let the top row of vertices be set A and the bottom row of vertices be set B. No vertices in set A are adjacent and no two vertices in set B are adjacent. This indicates we can color all the vertices in the top row one color, let's say blue, and we can color all the vertices in the second row the same color, just not blue, let's say green. This is a proper vertex coloring. All adjacent vertices have different colors, and we did this in the least number of colors, which is 2. This indicates the chromatic number is equal to 2, or chi of G is equal to 2. In fact, any bipartite graph has a chromatic number equal to 2. Next, we have a cycle on 6 vertices. Let's color one vertex blue, let's say here at the top. The two adjacent vertices must be a different color. Let's color both of those vertices green. And because we have a cycle, we will now just alternate colors around the cycle. So we have green and then blue, green, and then blue. Notice using just 2 colors, we have a proper vertex coloring. All adjacent vertices have a different color. Because we use the smallest number of colors, which is 2, the chromatic number is equal to 2. In fact, any cycle on an even number of vertices has a chromatic number equal to 2. If we have a cycle on an odd number of vertices, the chromatic number is equal to 3. Looking at our notes, we have chi of C sub 2n equals 2. This indicates the chromatic number of any cycle on an even number of vertices is 2. And then we have chi of C sub 2n plus 1 equals 3. This indicates any cycle on an odd number of vertices has a chromatic number equal to 3. And now looking at our third graph, let's color the inner vertex blue. The two adjacent vertices must be a different color. Let's color those green. Notice how the two remaining vertices are only adjacent to green vertices. We can reuse the color blue. The smallest number of colors needed for the proper vertex coloring is 2. Once again, the chromatic number of the graph is 2. And now looking at the last graph on the right, because it's more involved, we may want to look at the bounds for the chromatic number. And because the graph is not a complete graph given by k sub n, or a cycle on an odd number of vertices given by c sub 2n plus 1, the chromatic number given by chi of G will be greater than or equal to the clique number and less than or equal to del G, where the clique number is the size of the largest complete graph that is a subgraph of the given graph, and del G is a degree of the vertex with the highest degree from the graph. Well, looking at the graph, notice how the largest complete graph that is a subgraph of this graph is just K2, the complete graph on 2 vertices, and therefore the clique number is 2. Then looking at the degree of all the vertices, notice all the vertices have degree 3, which indicates del G is equal to 3. So using the bounds, we know the chromatic number chi of G will be less than or equal to 3 and greater than or equal to 2, which means the chromatic number is going to be either 2 or 3. Let's begin by coloring one of the inner vertices blue, let's say here. This vertex has 3 adjacent vertices that can't be colored blue. Let's color the 3 adjacent vertices green. Staying with the inner vertices, notice this vertex is only adjacent to a green vertex and 2 others that aren't colored. Let's reuse the color blue for this vertex. All adjacent vertices to this vertex can't be blue, and this vertex out here is adjacent to a green vertex, so this vertex also can't be green. We're going to need a third color, let's say orange. Let's color this vertex orange. And then going back to the inner vertices, this last inner vertex is adjacent to a blue vertex and a green vertex, and therefore it can't be blue or green. We will color this vertex orange. And now we have 3 remaining vertices outside. This vertex here on the left is adjacent to a green vertex and an orange vertex. Let's color this vertex blue. The next vertex going clockwise is adjacent to a blue vertex and a green vertex. Let's color this vertex orange. And this last vertex is adjacent to a green vertex and 2 orange vertices. Let's color this last vertex blue. We now have a proper vertex coloring of the graph, and the smallest number of colors needed was 3, indicating the chromatic number is equal to 3, which notice is in the closed interval from 2 to 3. I hope you found this helpful.